Institute of Physics, Bhubaneswar. He was a postdoctoral researcher in National Science Foundation at University of Puerto Rico, USA. He obtained his PhD in experimental condensed matter physics from Indira Gandhi Center for Atomic Research, Kalpakkam. His research interest encompasses multidisciplinary approach involving the synthesis, characterization, and application of 2D materials, metal oxide thin films, device physics, optoelectronic memory and neuromorphic computing, and Raman spectroscopy. So the title of the talk is Thermally and Optoelectronically Controlled 2D Materials-Based Devices for Bio-Inspired Neuromorphic Computing. Okay, so over to Satyaprakash. Yeah. Please, yeah, share the screen.
This one. Not quick. Okay.
What happened? Maybe he will log out and log in again. So let's just hold on. Please bear with us. I think he had some connection problems, so let him come back. Yes, you can start.
Okay. How it will go? Minus. No. Okay, thank you. Okay. Just 1 minute. Okay. So, so my screen is visible?
Yeah, it is visible. Pointer also is visible.
Okay, thank you very much. Thank you very much for your kind introduction. And I would like to thank Professor Panigrai for inviting me to give this talk. And not taking much time, I'll start my talk, which is basically on thermally and optoelectronically controlled 2D materials based devices for bio-inspired neuromorphic computing. So while I am discussing about this topic of interest, my plan of talk is the following. I will have a discussion on the motivation and introduction to 2D materials, introduction to neuromorphic computing, and optoelectronically and thermally controlled memory in 2D materials, and conclusion. So this is my group at Institute of Physics, Bhubaneswar, and today the talk that I am going to present before you is basically the work carried out by Shamir and Mausam, and our research activities at IOP. I will give a glimpse of that. And we are actually basically working on this oxide material, metal oxide material, metal oxide, and this 2D material, basically for memory and neuromorphic application and photodetector. So these are some of the recent publication I would like to share with you. And this is regarding this TiO2 based memory and neuromorphic application. And also on the parallelly, we're also working on this 2D layered materials for electronics devices and optoelectronics for logic and memory applications. And as stated by me, that it is important for me to give a overview about the importance of this 2D material. So before going to the importance of the 2D material, it is important to understand how this, the transistor that is present in our computer or cell phone, how they have been evolved over time. So this is the time scale over say 2005 to they say futuristic 2023, and you can see as the time passes, the transistor size is keep on reducing. That is what is observed by noted physicist More, and it is found that every 2 years the transistor size is reducing to half. So that means that we need, as time passes, we require more and more computing, thereby we require large number of transistors to be integrated into the circuit. But nevertheless, there is a limit to this, the scaling of this transistor. Now we are this 5 nanometer, channel length, and recently Samsung has, giving effort or putting effort to making 3 nanometer transistor. But there would be a limit because this technology based on silicon, and silicon, if you look at its, unit cell has a dimension of something like 0.3 nanometer. That limits the use of silicon in this transistor business. But then it is high time to also think about some other material, and importantly, material which is compatible to silicon. That means, which I say, when I say compatible, I essentially mean that we develop some material which essentially, when it comes to fabrication of those devices, it should be within the fabrication line of the existing silicon devices, so that we need not to think of new fabrication technique and other thing, because that is also require a time-consuming processes. So luckily, we have a material like graphene and this whole 2D material, which can be easily be grown in the laboratory scale, and the device that one need to make out of that uses the similar fabrication line of silicon. That makes life much comfortable if we think about this 2D material for future applications. Now, coming to this van der Waals solids, this starts with the graph. The journey starts with the graphene, and we have now a family of 2D material that consisting of graphene, 2D dichalcogenides, and so forth and so on. And you can see these materials has different properties when it comes to this band gap, and they are, whether it's metallic or semi-metallic, or whether they are insulating. So all sorts of, influencing property are being packed in this 2D material family. So that gives us a, new, that opens a new window for doing electronics with these 2D materials. For instance, with this boron nitride, which is a white graphene, is a completely a wide band gap material, and people are using it as a gate material. So this is very interesting class of material, which has very promising application as far as the electronic is concerned. And also, it is interesting to share with you that this 2D material, if you look at, the band gap, it covers from all the way from the ultraviolet UV range to say graphene like material, which is almost semi-metal, and it covers UV, from UV to visible to infrared. So depending upon what is the choice of our application, this material suit well to this electronic industry. Now, coming to the one of the most exciting engineering one can think of using the heterostructure, by heterostructuring this 2D material. Here, I have shown you some of the individual monolayer can be stacked together that gives rise to a new artificial crystal having a different property, which is combination of each individual layer. And that could be coupling of the property, giving rise to even more robust physical property. So that way, one can think of new artificial material using this layer material also. And one particular aspect of this layer material, which is interesting, is the optical property. And here I have shown that the interlayer exciton and intralayer exciton, when you do this, heterostructuring, particularly the vertical heterostructuring, and because of that, the interlayer exciton, which is otherwise not present, start appearing in this material, and which have great application in optoelectronics and lasing. For example, here I'm showing you a result at low temperature photoluminescence of stacking two different material, say molybdenum selenide and tungsten selenide. You can see here when the photoluminescence is measured at very low temperature. This is done on individual MOSC2, and you see this is the spectrum coming out of that. And when you do this purely on WSC2, this is the spectrum that one would get. But when you get the from the heterostructure, the photoluminescence, you see a drastic new peak is emerging, which is basically the intralayer exciton. So these are very interesting phenomena happening in this layer. The heterostructuring this 2D material. There is another emerging, interesting area is twisted quantum material. As you can see here, when two layers of graphene, when they are twisted with a small angle, you can see a new periodic pattern is emerged here. This new this type of pattern is called the Moore superlattice, and we know the electrons love periodicity. Whenever there is a new periodicity emerge, electrons show its new character in either in the transport property or in the band structure. So thereby, by changing the twisting angle between the two 2D material, one can get a artificial new system having different periodicity. So this is what is a very important topic of interest, topic of research nowadays. And now coming to this twistonic type of material, here I have shown that if you look at these two different material which are stacked together into a different angle, and you see the periodicity that is emerged out of that, and you see if you consider this high symmetry point A and B and C, and how the atoms are arranged, they are highlighted here. You can see these atoms in the atomic arrangement is quite evolving over A to B to C, then to A. So these are, as the atomic arrangement is periodic and changing, one expect there will be a lot of change in the electronic and transport property as well. So thereby, this type of materials are very interesting. And here I have shown whereby just by tuning the twist angle, one can tune the band gap of the material. So flexible electronics with 2D material is another area of interest, where you can see the cell phone, that conventional cell phone that we use, that sometimes get break because of when it come across the mechanical damage or something like that. This is because it's consisting of a glass, and the glass is covered with a conducting metal oxide coating, but these are very hard material, and they are not flexible, thereby it prone to get damage. but there could be a new material that coming with this kind of application where we can think of a flexible electronics coming out of is possible in future. But there is also an important application of this flexible electronics where in healthcare, where this can be also be used for monitoring various health parameter just by doing a tattooing on your skin. And to this, this 2D material can offer a great, this can offer a great choice because this 2D material can highly flexible. And as you can see here, some of the recent publication that shows that this material can be bent very, and you can see this twin boundaries over there, and they are quite promising for flexible electronics application. So I'm not going, these are the, these are the first area where this 2D material had its own advantage. Now coming to the synthesis of this material, one can synthesize this material in a laboratory using a CVD synthesis with chemical vapor deposition technique, where we routinely grow these the 2D material like MOS2, WS2. But here I want to highlight that while the making of this material is very important, because that will determine the quality of the sample and eventually determine what kind of application you're looking at. So this one should keep in mind that synthesis of this material is very important, because one has to take extra caution to find what are the factors that can affect your growth. Now, in our lab, we regularly synthesize this monolayer MOS2, bilayer MOS2. These are some of the picture that I'm showing you over here. And, just by changing the, carrier pressure, gas pressure, and various other temperature, RAM temperature, one can have different kind of growth parameter and have different kind of, 2D material coming out of the synthesis process, which is very interesting as well. Now, coming to the topic of interest that I will be talk about here, this is 2D material for future memory and neuromorphic computing. So, as I have already mentioned, that there is a need for looking beyond silicon, and 2D material could be one of the potential candidates which has the potential to, if not completely overtake silicon, but at least it can go along with silicon, giving rise to some, solving the future challenges that we are going to face. Now, in the era of artificial intelligence, we have now, experiencing the artificial intelligence and their product in our daily life. For example, self-driving cars, then a smart assistant, face recognition, and so on and so forth. And these kind of new devices coming into existence makes our life more comfortable. There is no question about that. But the bigger question lies that this kind of artificial intelligence that we use in our daily life, or we are been habituated in our life, they actually work on they run on the binary computer, the conventional computer that we are using. They are actually running on that with a heavy Python algorithm. So you need a a heavy. When I say heavy, that means it contains a lot of it's a huge amount of programming that is loaded into the system, and it requires a lot of processing, which involves the CPU, GPU, and that means the high power CPU and GPU, those are required. So that for instance, the present artificial intelligences things that we are using, in future, if you require to use them more efficiently, where more big data handling is required, for that we require more powerful CPU and GPU. But in contrary, as I have mentioned previously, that the size of the transistor is now decreasing. Now we have to think that beyond the conventional binary computing system. So now question is that, can we get anything that will help us in thinking beyond the conventional computing system? The one question come, or one solution could come from the bio-inspired technology, because as I am showing you here, that you can see here, we have inspired from biology and have made this, from this from the flight. We make the flight from the that we inspired from the flying of the birds, and also in the swimming suit that people use nowadays. It is being inspired from the the microstructure of the skin of spark that does not allow the bacteria to grow. And similarly, there are also bio-inspired technology like the bullet train in Japan. They have the nose of that train, the head of the train is similar. It have taken the concept from this kingfisher bird that makes that prevent the sound, the huge sound, coming out when the train coming out of the tunnel. So there are many applications that we always see that biology gives us some solution to our requirement. Similarly, so that people have been asking question that whether the brain can inspire, we can inspire from the brain to make some new computing. So that is what the brain-inspired neuromorphic computing is all about. So what is this neuromorphic computing? So it says the hardware design inspired from the biological neural architecture and computational occurring inside the brain. So here the point I want to make, here we are looking at the concept through which how the brain, inside the brain, how the memory is happening and how brain is processing those memory. These are the two crucial factors that we are looking at when we are considering the neuromorphic computing concept. So for that, we need to have a look in the conventional computer, which is digital computer. And you can see the digital computer has a memory and a CPU. And this memory and CPU, they are separated by each other. They are not in the same entity, they are separated. So because of which, the data goes from CPU to memory, memory to CPU, so this consumes a lot of time and also consumes a lot of energy. So this, but if you look at the brain when you look at the brain and examine it, you'll see the CPU and memory, they know separate CPU and processing unit and memory. They're all packed in the same brain. And that makes the brain so interesting for studying this neuromorphic computing. If you do the reverse engineering, for example, if you do the reverse engineering of the brain, we can get some idea that if we can make some artificial neuron and then can study the biological learning behavior, if that can be exhibited by this artificial neuron, then one can think of using this artificial neuron for neuromorphic computing. So why neuromorphic computing? I will give a small example over here. Here is the human brain, which contains 10 to the power 11 neurons and 10 to the power 15 synapses. And importantly, here the point to remember, it is analog and also it consumes only 20 watt of power. In contrary, if you take the one of the most advanced computer of IBM, so it contains only 8 into 10 to the 4 neurons, and yet it consumes 40 kilowatt. So that makes a lot of difference, and people and that makes people to think about to borrow the architecture of the brain and utilize it and to develop some artificial neurons. So now let's look at the brain as a whole. If you look at the brain as a whole, it is inside the skull, and if you look inside the brain, it has a lot of neurons. They're quite compact in structure. And if you look at the individual neuron, the individual nerve cell it contains a lot of branching, and each branching they communicate to other neuron just by in physical contact to each other. And I will show you in the next slide this physical contact, I mean that one neuron from one side and the other neuron other side, they're actually not exactly physically in contact, rather there is some gap between them. And when the stimuli come from one side to other, they release some kind of chemical, thereby it changes the potential energy or potential difference between the two neuron, thereby making some kind of memory, permanent or short-term or long-term memory, depending upon how frequently one learn the things. So this is a schematic diagram I'm showing you how particular this biological neuron or biological synapse work. So if you look at what is important in a synapse is the plasticity. Plasticity is something that plasticity is the nervous system to change. That means if you learn something, there will be a definite change in the potential in this presynaptic neuron and postsynaptic neuron. That is a kind of change in the potential between these two that makes a permanent change in the potential, thereby making it a memory. But if you are not using something for a long time, slowly that potential degrade, making it depletion. So you will not remember things. Then again, when you learn something, then again that change in potential occur. So that is how a plasticity is important in a synaptic plasticity is important for in biological system. But it is important to remember that we are looking to create such kind of artificial neuron in using these materials. But what is parallel? What is the connection between these two? Here there is a change in potential that occurs that may stay for a long time, depending upon how fast or how intense is the learning process. But here, in terms of in case of artificial neuron, artificial synapse, what will happen? We try to change its conductance by applying a voltage pulse or some kind of signal, outside signal, which you will discuss later. So this is the this is what is the similarity between these biological and artificial synapse. The whole idea is to change the conductance level, different conductance in this system. So here what happens when the signal comes, you can see here when a signal comes, it from the presynaptic neuron, that means which carries the signal, it releases some kind of neurotransmitter. It goes and attaches to the receptor side, and the receptor side opens, and the receptor side opens up. Then the sodium ion pump into the presynaptic neurons, and thereby there is an imbalance in the potential, and that potential you can see here, there is a change in the potential. This potential change is what people call is the memory. So now, having some understanding about these artificial neurons, about these neurons, now we'll be focusing on the artificial neuron. Artificial neuron basically is a material. We have a material over here connected by two contact, and here the point of interest, the material of interest, we should be able to change its conductance by applying a different external trigger. So that is how they are, there is a link between the artificial neuron and biological neuron. Now, the criteria for artificial synapse. So the synapse should have a memory. That means when you apply some external pulse or external stimuli, then it must respond. It must respond in the sense that it should change its conductance. It should change its conductance. And it should one-to-one respond. That means it should specifically respond to a particular a degree of stimuli. Then synapse should be small, and that's natural. If we want to make a device out of small, this material, this has to be small so that we can have a high density of this devices. And synapse should be plastic. Plastic in the sense that this whatever it has the change in the conductance, if we do not want to use it, we should be able to erase it also. That is how is the plasticity is all about. So now we'll discuss about the optoelectronic artificial synapse. For this, first I would like to discuss about a photodetector. A photodetector is something when you switch on the light, the blue color is the light, and the red color here is the in the response. It responds to its response in terms of the current. You can see here when the light is off, there is no current. When the light is on, you get highest current. When the light is off, again it goes back to the baseline. But it is something like a 0 state or 1 state. But if you have a a photodetector, but a different kind of photodetector, in the sense that when you switch on the light, this current goes off, current goes off. But when you switch off the light, instead of coming directly to the ground state, it stays there. Okay, so this is what we are looking at. When it stays there for a long period of time, that means it responds to light, and depending upon whether it's a light intensity or light wavelength or light, the timing, timing of the exposure, the current that it stays can varies. So thereby one can have a change in the conductance in those material just by changing the different light intensity. So here, this when you give this optical stimulus, if it is less frequent, the system can undergo a short-term plasticity because it will not persistently stay for a long time. But if you do a frequent optical stimuli, then a long-term plasticity can be achieved, which I will discuss that. So for this, we chose this monolayer MOS2, which is CVD grown, and then we make this transistor using this photolithography system. Then we characterize this material or this transistor under the illumination of light, different wavelength. So what is shown here, when you switch on the light, you see, when we switch on the light and you switch off, it does not go back to the ground state. It stays there. This is what is because of your persistent photoconductivity. And why this persistent photoconductivity arises? It is because of the localized random potential fluctuation due to the trapping of the photogenerated carriers results in the persistent photoconductivity. And this is what is required for our memory. One can consider this change in the persistent photoconductivity as a memory. And remember, this can be achieved in a sequence that this can be this is not digital, this is analog. One can get one state here, one state here, one state here, one state here. Then can have an infinite number of states depending upon how you control the light input. So here I am showing you the variation of the light color. You change the light wavelength from the red, green, and blue, and you see how it responds to this light. Here we have varied the power of the light as well as the timing up to which we are exposing the light. In either case, you can able to change the photoconductance. You can see the photoconductance is responding quite well to the power, to the time, as well as the wavelength. So these are basically the external, can be used as the external stimuli like the biological one, and it can change the conductance of this material, which can essentially resemble the biological conductance change in the synapse. Now, basic synaptic function. So before we classify a material or the device to be useful for neuromorphic computing, some of the basic biological or the learning training has to be qualified. For example, if in biology, in particular in a synapse, biological synapse, if you give a continuous pulse, okay, of same height, then it is the input pulse that is received from this neuron, and then in response you get the current in the other part, the postsynaptic. Then what will happen when you are applying a continuous pulse having some say time difference delay between them, the depending upon the time delay, which is important, then in response to that, the current in the postsynaptic neuron keep on increasing. It's very interesting. This is biologically established. And you can see here, when we apply the similar thing in our, say artificial, MOS to synapse, you see here, when we switch on the light, it goes to this state, then it switch off the light, then we again switch on the light, and each time we switch on the light, you see when the pulse of light you are applying, you see the each successive pulse makes the current increasing. From here to here, it is increasing. Like the biological thing you are getting the similar thing here. But point to be noted here, what I mentioned previously, the timing between the two pulses, the time between the two successive pulses is important. If you change the successive timing, then you will get a different result. For example, if the time interval you keep on increasing, you see the percentage in the chain you keep on decreasing. This is what is already established in case of biological neuron, and which is very similar things we are getting in case of our artificial neuron, in this MOS2 artificial neuron. Similarly, it's a very interesting result. When you apply a constant pulse, say this for here, this is a pulse is applied, pulse train is applied. As you apply this optical pulse train, you see the current is keep on increasing, which is basically changing its conductance. Now, this is what it is called long-term potentiation. You keep on applying the pulse, that is something, some memory is going there, and it keep on increasing its conductance. And you can see the current is increasing. But in case of memory, what is important, we should be able to erase it. So how you erase? When you apply electrical pulse, you see the potentiation is long-term potentiation is achieved by the optical pulse, and the erasing of those memory is achieved, is called long-term depression, is achieved by applying a electrical pulse, which makes this material very interesting. Now, another important thing that I would like to discuss here is you change the number of pulses. When you change the number of pulses, for example, 5, 10, 25, 50, it is in varied, you can see here the persistent photoconductivity is also getting changed. That means, as I mentioned previously, it responds to it. That means whenever you apply this 5 pulse, it will always be here. Whenever you apply a 50 pulse, it is always to here. That way, you are storing the information of the external stimuli in these devices. Similarly, when you change the pulse frequency, you can see here there is a consistent change in the photoconductivity. So this essentially tells us this particular artificial neuron can be integrated, can large scale, it can be made, and they can be connected to each other to perform a specific pulse detection. For example, they can be used for image recognition. And what is important, another important experiment that we have carried out, which is called Pavlov's associative learning behavior. But here it is optical version. What the experiment is all about? Suppose you have a food and a dog. When the food is there, that means you are training a dog. That means when you are training it, when the food is there, the salivation will come. And suppose you only rang a bell, there will be no salivation. But when you mix together food with the bell, the dog will respond. Then you make the dog train. So that means you continue this process, bell and food continuously, and whenever you put that means it's a training of the dog, and the dog will salivate at a particular time. But now, after giving training, you remove the food and only ring the bell, the dog will start salivating. But for a long period of time, once the dog knows that there is no food available, then no matter how much bell you put, the dog will not salivate again. So similarly, we have done the similar thing with this artificial synapse. Let's see how it responds. So what we have done a pulse. We have illuminated it with a UV light, and we have defined a threshold, say threshold current over here. And this is, you illuminate light and you switch up, and you see this is the threshold current. Then you use a red light. And the red light, as you know, it is not energetic one, so it will not go to that threshold. It is like ringing a bell, and this is UV light like a food. Now, for the food, this device is responding, but for the bell, it is not responding. But if you train them, you combine a red with the UV light, and you train the device, you see, as you do the pulsing, I mean the a combination of the violet and the red light, violet and red light, you see after a certain time or certain repeating the experiment, you see it will now goes above the threshold. That means it is now a training process like the dog we have seen. Now you switch up the UV light now for a long, for a several, large period of time. You can see it is still responding to the red light, similar to the dog responding the food to the bell when the food is not there. But for a long time, if you leave it, it then goes below the threshold frequency, threshold current, and it will not respond to the red light, similar to the dog which has forgotten the response to the food, because if the food is not there, it will not respond. So we have demonstrated this Pavlov's associative learning behavior in our device, which is the optical version. Excuse me. One important and interesting feature is here is reconfigurable logic operation. We have used both the optical and electrical response as the input to show the same devices can operate a NAND, a and or operation. You don't require two different set of devices. Same devices can do the same thing. But what is the trick behind it? That you have to, once you are done with the AND gate, you can go to the OR gate by illuminating a UV light. It resets the system. And once you are in the OR gate, you apply a voltage pulse, it takes it to the AND side. So this is very interesting result that we got. Now I'll quickly discuss about the thermally controlled artificial synapse. So here I am showing you some of the basic characteristics of a hysteresis curve that we get in a MOS2 transistor. You see, while going in the forward direction, this is the while we varying the VG backgate, and you see the current how it is responding. But while coming back, it is not following the same path. There is some kind of hysteresis involved. And this hysteresis in particular, this is in air, but if you make in vacuum, is the hysteresis still there, it reduces, but it's still there. So, but this is not good for the electronic application, particularly when you have 0, 1, 1 or constant, because this threshold voltage instability is there. So for that, if you use a pulse voltage, we have demonstrated by using a pulse voltage, you can completely irradiate or completely remove this hysteresis, which can be achievable. But this is as far as the hysteresis minimum is concerned, which is required for the high performance transistor, integrated circuits, sensing applications, LED and optoelectronics and smart electronics, because you don't stability in the threshold voltage. But in some cases, this is good. I mean, having a hysteresis is good. That means this history, if you have a large hysteresis window, one can think of this as to use them as non-volatile memory. I will show you in a few slides how we have take this opportunity and use this as a non-volatile memory. So these are different type of memory concept that can be associated with these 2D materials, like contenders memory and heterostructure based memory and optical memory, which I have just discussed. Now there is another class of memory one can think of, which is ion-gated memory. I will discuss more about this in detail in following slides. And you can see these are the thermally controlled. We'll discuss about how this temperature plays an important role when it comes to memory associated with this MOS2, particularly where a large hysteresis window is involved. So these are the basic characteristics of this MOS2 that transistor that we have made, and we are regularly doing these transistors in our lab. And what is important is a very striking feature I am going to discuss here. You see, this is the hysteresis characteristics of a monolayer MOS2, which is grown without a NaCl involved. Because while we grow the sample, two category of approach we have, where one category where we use some kind of salt, and in other we do not use the salt. And when we use this, the advantage of using salt is that because it acts as a catalyst and it grows a large area MOS2 when required. But here we have grown this sample without NaCl, and you can see here, as you increase the temperature, say from 250 to 450, you can see here it is always a clockwise hysteresis. It goes like this. In case of, by considering the charge trapping and detrapping, which I'm not going to discuss in detail because of lack of time. But interesting things comes into picture when you compare this result with the sodium chloride assisted growth grown MOS2, and you can see here from 250 to 450, when you grow this, when you characterize this material, you see it shows a change in the hysteresis. That means initially at the low temperature it was clockwise, then at high temperature it suddenly become anti-clockwise, which is something very interesting. And this can be explained because in terms of ion dynamics, what is different between this and this is that when you grow this material in case of sodium chloride environment, the sodium goes into the silicon dioxide, and thereby this sodium activates or become mobile, more mobile at high temperature, and they contribute to the conducting channel, and thereby you see there is a drastic change in the in the hysteresis. It become a reverse hysteresis or anti-clockwise. Previously it was anti-clockwise, now it become a clockwise hysteresis is achieved. You go like this, then come like this. So now what is important here to discuss is the following. So if you see carefully the temperature range that we have discussed previously, when the system is you apply a pulse voltage of the gate voltage. Gate voltage, you make it a pulse. Here we have shown a pulse voltage of say 30 volt we have applied, and you measure the drain current, measure it over time. And you can see here this transient graph tells you many things. When it is at 300 Kelvin, you see, suppose we consider this read voltage or read current, and this is write current when the voltage is when the pulse voltage is there. You see here the read, both the side read R1, R0 or R1, they are same. But when we increase the temperature and goes up to 400 Kelvin, you can see a dramatically change in the read current. You see, here it was both the side read is same. Now, as we are at 400 Kelvin, you see now the read current is now picking up and it is higher. Now when 450, it is much higher, which is consistent with the previously where I have shown it undergoes from a reverse hysteresis. Now, taking this as a advantage of memory, what we have done, we reset the system first, then we apply a pulse, a voltage pulse, and the voltage pulse of say around 30 to 40 volt, and you see what is happening as you increase the pulse voltage, as you increase as the pulse train is applying to this material or the devices. You can see the read. Look at the read. The read is keep on increasing. The read current is keep on increasing. That essentially means it resembles with that of the biological synapse, where you apply a pulse train, and you expect the current to increase, which is what is happening here. And importantly, having achieved this this memory, one can always think of erasing this. So you apply a negative gate pulse, and you see here immediately it starts erasing. So this is a very systematic study that you have carried out. And I will not go detail about this because of time. And now I'm going to discuss some results about our recent result about this WS2 transistor. The WS2 transistor is interesting because unlike MOS2 transistor, where I have shown the hysteresis is not that wide, but here the growth process is same. Only thing is that we have kept the substrate to the precursor distance closer. By doing that, we have pumped or injected number of sodium atom more into this silicon dioxide substrate, the one I am showing in the cartoon. And it has a direct effect on its hysteresis. You can see here, unlike the most sample that was shown, here you can see when you increase the temperature, you see it shows a wide range of hysteresis, correct? And this is the plot between the hysteresis width, which is basically the change in the voltage from say from here to here, and you can see the current ratio. That means at 0 voltage, what is the difference? What ratio of the current? You can see that one, and it increases with the increasing, both increases with the increasing temperature. This is a very interesting one. Now, considering this hysteresis curve, we will try to analyze or understand what makes such hysteresis so wide. So now what we need to do, let's now do an experiment by coming from, say, a positive voltage, a positive bias, say from 40 volt, then go to the negative, and then do another experiment from doing from here. Let's see what is happening. So here is the positive side. You apply a positive stress. That means you come from positive voltage, then go to the negative side. That is in the top one. And wait while applying this positive voltage, the positive stress, wait for different time. And waiting, these are the basically waiting time before you start the experiment by applying the 40 volt. You can see here, while we applying a different wait time is more increasing, you see the current in the current, the hysteresis current is also increasing. But this is because when you are applying with your wait time is more, you are actually pumping more mobile sodium ion near to the interface, and thereby they contribute or they additionally release some kind of electron cloud around them into the WS2 channel. Thereby they increase this trend is noticed. Similarly, if you look at an interesting result is observed while you do the negative stress. You apply the negative stress on the -40, now go here and wait for the similar time, and you see there is no change in the curve, where you get this large change here. And this is basically because when you apply a negative stress, sodium ions actually they are pumped out from the interface and having no contribution to this conduction channel. Now, another interesting result that I would like to show you in that you do this experiment, you go in the forward direction, then wait at a particular voltage, particularly in the positive cycle. You stay here, don't do the experiment, just stay, just hold the experiment there, and wait for, says we waited for 6 hours for this particular experiment. Then we do the experiment. After 6 hours, when you hold the experiment and do, we see the backward current increase, but we do not know during this 6 hours how the real time current change. That I will show you. And interestingly, while this is say 20 volt, the stay at 20 volt, here the state around say 10 volt or so, and here the state at say 0 volt, and here the state at negative volt. And you see a dramatical change in the hysteresis behavior is observed. And as I mentioned, during this 6 hours, while we hold the experiment, we are doing another experiment. That means we are doing a transient experiment. We are measuring the time spent, time versus the ID, how the current is changing. Once you are at this stage, how the current is changing. You see, the current is increasing continuously for say 20 volt, 10 volt, and 0 volt. There is no change, and that's why it is coming in the same thing. But for -20, -10, it decreases, and here see the. So this essentially says the mechanism that we are proposing, that is a sodium-based ion movement that facilitates the observation of large hysteresis window, that is that is indirectly being probed by these techniques. Now coming to the cyclic variation, we have done a say 100 cycle variation by just changing the sweep rate, you can see here there is a narrow change. You see how close or how narrow is these chains are. They're quite repeatable and quite consistent. That gives a that gives a indication that these materials can be used for a long-term memory application. And for each cycle, say from the forward and backward, we have calculated the the mobility, and mobilities are quite consistent. And we have calculated for forward, we have calculated the V threshold, and for the backward, we have calculated the V threshold. These are also quite consistent as seen from this figure. And we have done also device to device variation, which is we have done for experiment for the 8 different devices, and these are quite consistent. And now coming to the very important observation that we have seen, when you give a pulse voltage of say 50 volt to these devices, and once you apply a gate voltage of say 50 volt, and you change the conductance of the system, and once you change the conductance of the system, you measure over time how long that conductance stays without unaltered. So we have applied, we wait for say 10 to the power 3 seconds, and you see there is a little decrease or small decrease in the current. And if you leave the system, if you extrapolate it, and people, this is the way people are reporting. And if you extrapolate this, result, you can see these devices, once goes to a conductance state, can stay even for a 10 years. So which is kind of, because we cannot test it for 10 years for the devices, but this is how people are doing. And this shows this device is quite robust. Can once a memory state is achieved, it can stay for a long period of time, and they are promising for application, memory application. What is important here? We have applied a pulse voltage, say pulse train, say 5 volt and minus 40 volt, and we have read this. And you see, when you do this experiment, for a 5 volt read, you see the current is picoampere, and it is consistent over a period of 40 cycle. Is a small current of picoampere, the state can be the state repeat itself, which is very good as far as the memory is concerned. We have achieved a 6-bit storage capability. What I mean by that? That means when we apply a different pulse train, say we have applied a 5 voltage, a 10 voltage, 20, 40, and 50 voltage over here, and you can see here there is a change, consistent change in the conductivity of the system, and each conductivity. Once you achieve each conductivity, you can see how long this conductivity can stay. We have done it for say more than 1,000 seconds for each conductance state, and we could able to achieve 64 states, memory state, which is quite impressive. Now I will try to show some of the more neuromorphic application of this WS2 transistor. So what we have done, so just to recall that how the biological response, or when you have this external stimuli goes from one neuron to other, it changes the potential, and this is the potential is the key for the memory. And here we have shown just by applying a different pulse width, say for 0.1 to 15 seconds, we can systematically change the conductance state of this transistor. And this is the pulse of the this is the pulse of applied pulse of the gate voltage, just to remember. So by changing the pulse width, one can change the conductance state, which is very similar to what is achieved in case of a neuron, where the conductance the conductance changes, and thereby a memory state is achieved. Similarly, we have applied a voltage strain of 10 volt like that, and a negative voltage strain of 20 volt. While we apply a positive volt of 10 volt, a potentiation occurs. That means a continuous increase in the conductance we can observe. And when you apply negative voltage of 10 volt train, we can see the depression. That is, this is erasing, and this is potentiation is basically the learning, and this is forgetting. So similar thing we have done for the MOS2 also, and we are getting a nice learning, I mean, the potentiation and depression, which is quite, linear, which is consistent, which is linearity is required for, for better image recognition or some kinds of application in that, with that concern that. So what we have done by extracting the data, that means the change in the conductance over the pulse number, and the change in the conductance when you are erase processing there, you get you feed it and find this input, these values, and these values are important for when you do this a simulation. These values are important to tell these are the input value that you take from the device, and we give these inputs to a PyTorch program. That PyTorch program taking these inputs, it try to simulate or try to get the best way this device can recognize a number. Here we have showing for a number say 9, and and we have shown here how good it can recognize a number for a given number. It can recognize something like 90, more than 95%, which is consistent with the theoretical value. And you can see here with a desired output, suppose the desired output is say for 0, the inferred output must be 0. That means if you are dealing with 0, the device should recognize it as a 0, not otherwise. Then you see for this program, by taking these inputs parameter, we could able to see that whenever there is two numbers, say 6, we want to how well this device recognize 6, and you see it recognize quite well with the accuracy, say more than 90%. So these are the potential result that we got using these 2D material as memory. And to conclude, this 2D material optoelectronic synapse is fabricated in a transistor configuration by exploiting the persistent photoconductivity of the device, the learning behavior of the biological brain, such as these are the learning behavior, which I did not, these are technical terms, which is the long-term potentiation and short-term memory, long-term memory. This can be achieved successfully, achieved in these devices. Then we could able to do the logic operation in the same device by using the same device is used for using this and OR gate. And we also demonstrate high temperature memory and neuromorphic application using MOS to WS2 by introducing ion driven interfacial charge dynamics. So with this, I thank you all. If you have any question, please, I'll happy to take.
If anyone have some question, please ask.
I have one question.
Yeah.
Thank you for your talk. Could you please name the software packages used in modeling simulation of numerical experiments?
Yeah, so this one we have used this PyTorch.
Okay, so any other additional packages?
No, we have
apart
not.
From...
No, we have not used any additional packages. We have used PyTorch because my students, they get into, I mean, they learn it last 1 year about the PyTorch, and we have been using this PyTorch.
So do we need to perform these numerical experiments? Do we need very high power computers, or is it just simple laptop can be used to model and do simulation?
Yeah, we are using simple laptop because they have used a laptop to use it, I mean, to evaluate this one. In fact, we have this in our system, in our IOP, we have also high performance system which can be connected to the laptop and do it.
Thank you.
Are there any more questions?
So I think there is no more questions. So once again, thanks to you, Professor Sahu, for this wonderful talk. So
Thank you
our
very
next session will start from 3 p.m. With the talk by Professor Arun Kumar Pati. So thank you, everyone. Please join at 3 p.m.
Thank you. Bye.
Bye.
Also, there is a tutorial starting from 4 p.m. today. So we have updated in the schedule. So we expect the participants to be present in the tutorial. Thank you.